So good evening all. I welcome all of you to the day 2 of our program on optimizing next gen computing for smart system development. So today also we are having two sessions. So the first session is from 6 to 7:30 and the second session 7:30 to 9. So Professor Saroj Kumar Patel sir is going to deliver these two sessions. So first session is going to talk about single variable optimization techniques and the second session sir is going to talk about multivariable optimization techniques. So it's my privilege to introduce Professor Saroj Kumar Patel sir to our participants. So Professor Saroj Kumar Patel sir is currently working as a professor in Mechanical Engineering Department of NIT Rourkela. So in NIT Rourkela, he has discharged various responsibilities like Dean Academics, Dean Student Welfare, Registrar, Chief Warden, Head of Training and Placement, Head of Central Workshop. Sir was also a project officer at NTMIS, National Technical Manpower Information System for the entire state of Odisha, handling all the government and the private engineering colleges, engineering diploma schools and pharmacy colleges of the state. Sir completed BTech in Mechanical Engineering from NIT Rourkela in 1985. Initially, Sir had industrial experience with Hindustan Aeronautics Limited, Koraput Division, Sunabeda for 5 years before joining NIT Rourkela as a faculty in Mechanical Engineering Department in 1990. Sir obtained MTech degree from IIT Madras and PhD degree from IIT Kharagpur. His broad areas of academic interest are optimization, statistical quality control, operational management, and machining. Sir has supervised many PhD theses. Sir has published more than 90 research articles in peer-reviewed international journals and more than 70 conference proceedings. Sir has published 3 textbooks on topics like basic statistics, operation research, and MATLAB. So, with this brief bio, I request Saroj Kumar Patel sir to start his session. Over to you, sir.
Thank you, madam, for your nice words. And I welcome all the participants for this lecture. So this lecture will be divided into two parts. First, we'll discuss all the methods which are used for single variable optimization problems. And then we will go for a little higher, more complicated one, that is the multivariable optimization problems. So let us start with the single variable optimization. So is my slide visible?
Now it is not visible, sir.
So entire screen, let me see. Allow. Is it visible now?
Yes, sir. Yes, sir. It is visible, sir.
So we'll first discuss about single variable optimizations. So this is my introduction, my name, and currently I am HOD of Mechanical Engineering, and I have been working in this NIT Rourkela for since 1990. So it would be 35 years I have worked here, and I have 3 more years to retire. And before joining this teaching profession, I was working in HAL Sunabeda, Hindustan Aeronautics Limited, Koraput Division for 5 years. And you are free to contact me even after the completion of this course. So this is my email ID, skpatel@nitrkl.ac.in. And even I am quite active in WhatsApp. You can also ping me at my WhatsApp number. This is 9437 48 49 51. And I'll be more than happy to clarify any of your doubts during today's class or even after class is over, lecture is over. Anytime in your career, any doubt on optimization, I'll be happy to clarify your doubt. And whatever I'll be discussing in today's class, both single variable and multivariable, all these lectures are available on YouTube. I have 2 playlists there. One playlist is on operation research. So there you can find all the video lectures on linear programming, transposition problem, game theory, decision theory, then aggregate planning, job scheduling, forecasting, etc., etc., even queuing theory. And there is a second playlist. There is optimization method in engineering design. So there you can find all the lectures on optimizations, including today's whatever I will be discussing. So you can search in my name in the YouTube, Saroj Kumar Patel, and give a keyword either optimizations. You will be getting my video lecture. So around 30 to 40 lectures are there. You can have a look on this whenever you find time. And the direct link to my video lectures is this one. The last line is giving the link to my video lectures. Now, for this optimization course, the best book that I have found out, there are many books, but the best book and the simplest book and the most fundamental book is the book by Professor Kalyan Maya Dev. That is Optimization for Engineering Design, Algorithm and Example. So he has already published 2 editions, so you can refer the second edition one. And it is Prentice Hall of India Publications. You should read this book. And Professor Kalyanmaya Dev, as you know, he was a very renowned professor in the area of genetic algorithm and optimization techniques. Earlier, he was a professor in IIT Kanpur, and now he has switched over to some foreign university in United States of America. And these are other books in the area of these optimizations. I have also written a co-author one book along with Professor Alam, and this is a computer book in MATLAB. So a computer coding in single variable problems in MATLAB you can find in one chapter of this book. There is advanced guide to MATLAB, practical examples in science and engineering. And Jasveer Arora is also a good book. Then other books are Ranjan Ganguly, Lindfield, 2 books they have written. Then R.V. Rao of NIT Surat has also written a book. Then S.S. Rao is a standard book, textbook. Then Ravindran and Venkatraman. As Madam has told that I have written a few textbooks, so those books are this one. So this is the MATLAB book that I have co-authored. Here you will find out the computer programming of single variable optimization techniques, and the language that I have used is MATLAB. This is the book on operational research that I have written, and this is, you can find all this linear programming, transportation problem, game theory, etc., etc. Then I have also written a book that is basic statistics. Okay, now let's try to understand what is an optimization problem. So an optimization means either if the objective is a desirable one, like let's say profit or sales revenue, or let's say material removal rate, or the comfort in riding any automobile, or you let's say the mileage of this one. So these are all desirable, and we will be more and more happy if the value of this is higher and higher. So there we will be maximizing it. So we will write down an objective functions. So f is the objective function, and it is a function of a number of variables. There is x1, x2 up to xn. So the given a problem, first we will write down what is your objective. If it is MRR, then MRR is a function of, let's say, speed. X1 may be the speed, x2 may be the depth of cut, and x3 can be your feed. Then f of all these 3 variables will be your material removal rate. So in this we are going to maximize it. Then subject to a number of constraints. So one set of constraint will be inequality. So the left hand side will be as and when we will try to, and this will be also a function of this independent variable, or we call it decision variable. Why decision variable? Because those values we are going to decide it whenever you are going to design it. So the left hand side of this inequality would be consumption of resources, and this B1 will be the maximum availability of the resources. So because resources are finite, so within the available resources, how much we can consume, and this consumption cannot exceed the maximum availability. So that's why the appropriate inequality would be less than or equal to. This is for resource 1. Similarly, for resource 2, the second inequality. So like this, if we have m number of resources, there will be m number of constraints will be there. And also in some of the cases, we expect that it has to be left hand side has to be exactly equal to the right hand side. So in that case, it is equality constraint. That means a number of constraints can be divided into two categories. One is inequality type of constraints, another is equality type of constraint. So normally, if the objective is to maximize, this inequality will be less than or equal to. And then finally, we have to decide the range of all the unknown variables. So x1, what is the upper limit? What is the lower limit? Lower limit is x1L, lower limit, and x2, x1U will be the upper limit for x1. Similarly, the unknown variable x2 also the lower limit, upper limit. So x2 must be greater than or equal to upper limit x2U, and greater than or equal to lower limit, there is x2L. So for each and every unknown variable, we have to write down their domain. This is a search domain, the lower limit and upper limit. So thus, any optimization problem will have three components. The first line is your objective functions, and we have to write down whether to maximize or minimize. And the last line would be your range of the unknown variable. That is the search domain. And in between, we'll be having a set of constraints. And this set of constraints will be divided into two categories. One is less than or equal to, other is equal to. Now, if the objective is like, let's say it is a cost, then we should not maximize it. As common sense says, we have to minimize it. And if the objective is waste, let's say the tool wear has to be always minimized. So in those cases, the objective will be, instead of maximize, it will be minimized. So in that case also, the format will be exactly same. Only difference would be that this less than or equal to should be greater than or equal to. So if we can write down a given problem in this format, typically this is called a optimization problem, which is either a maximization or minimization problem. So thus, any optimization problem have three components. One is objective function, the top line, that we write down as function f of the unknown variable x1, x2 up to xn. These x1, x2 up to xn, which are the unknown variable, whose value we are going to find out, are called as design variable or decision variable. Variable for which we are going to design, or the variable which we are going to decide. So decision variable. And these constraints G1 to Gm, the inequality type of constraints are constraints, and H1 to HP are P number of equality constraints. So we have three components in any optimization problem. Now this last line, these constraints are either equality constraint, which we denote it normally as h of x, the function h, and inequality constraint is the function g. And these functions are called functional constraint. And the last line, that when we specify the upper limit and lower limit for every decision variable, which actually tells about the search domain or the boundary for the variable, these are called site constraints. The last line is actually site. It decides the zone. It decides the upper side and lower side. And in between, whatever you write down, that H constraint and G constraint are called the functional constraints. And the top line is called the objective function. So we have broadly two types of constraint. One defining its domain, the last line, that is site constraint, and another is functional point of view, the consumption of resources point of view, the constraint. That is again of two types, equality and inequality. If you have any doubt, please stop me in between. Huh? Okay. Now let us classify these optimization problems. So if we have only one objective, then we call it single objective optimizations. Let's say we are going to maximize only material human rate, then it is single objective. But if you are going to maximize material human rate and also maximize surface finish, then we have two objectives there. Then in that case, it will be multi-objective optimization problem. So based on number of objective, this can be either single objective or multi-objective. In single objective, we have only one objective function f, but in multi-objective, we'll be having more than one objective function f1, f2, f3 like this. Then the number of unknown variable, that x1 to xn, if we have only one unknown variable, we call it single variable optimization. That we'll study first. And if number of variable, there is n, is greater than 1, at least 2, then it is multivariable optimization. x1, x2, at least, then it will be multivariable. Or x1, x2, x3, multivariable. More than 1 is multivariable problem. Then in some problem, there may not be any constraint. I mean, only top line will be there, only objective functions. So that will be called unconstrained optimizations. But if we have constraints, then that will be constrained optimizations. Sorry, let us take it to the PPT mode so that will be clear. Presentation mode, okay. Now I think it is better for you, right? Hello? Does it, from visibility
Yes,
point of
sir.
view?
Yes, sir.
Okay, okay.
Yes, sir.
Then, depending upon the type of objective, the problem can be either minimization or maximization. That already we have discussed. If it is a material human rate, we have to maximize. If it is profit, we have to maximize. But if it is a cost loss, then we have to minimize. Then depending upon the function that you use, either in the objective function f or in the constraint function on the left hand side, either gx or hx, if maximum power of any unknown variable is 1, then this is a linear problem. But if maximum power of the unknown variable, any of the unknown variable is more than 1, or if it involves with a trigonometric function, sine, cos, all these things, or logarithmic function, then this is a non-linear problem. Then depending upon the type of objective function, it can be either integer programming problem where the decision variable x1, x2, xn can take only integer values. If the values of unknown variable can take any real value, means even fractions, that we will call real value programming problem. But if it can take integer as well as the real value, then this will be called a mixed integer programming problem. Let's say the objective is to, let's say, how many number of brand of a car company is going to manufacture. In that case, the unknown variable will be number of units. It will be only integer programming. But let's say a cement manufacturing company. So there, the quantity of which brand of cement we are going to manufacture. So this is a kg of cement. So in that case, it can take any fraction value, either 2.3 kg or 2.4 kg. So any fraction value it can take. Then relationship among the decision variable. If decision variables all are of independent of each other, means x1 is independent of x2, then this is a static problem. But the x1 is also a function of, let's say, x2, they are dependent, then this is a dynamic problem. Then regarding the solution, this ones, we can either solve it, traditional methods are there, or there will be non-traditional method. In traditional method, if we use the calculus method, that already we learned it in our +2 level, the derivative, using the derivatives, we can find out the maximum or minimum value. So if you use that method, we'll get the exact solution. 100% accurate result will get it. No error. And that method is called analytical method. That already we know it in our +2 level. But there are some problems where it is not that simple. The functions are not simple. We cannot just take the first or second derivative equal to 0 and then we can solve it. So what which are those problems also we can get the solutions, but that is iterative procedures. Iteration after iterations, we will find out the solution. But here it will be not 100% accurate result. These methods are called numerical methods. It is a iterative methods. So we will discuss both. To start with, we'll discuss first the fundamentals analytical method. Then we'll discuss the numerical method in today's class. Then recently, many nature-inspired numerical methods are being proposed by the researchers, like genetic algorithm, simulated annealing, particle swarm optimization. So these are all non-traditional methods. These are all based on the natural phenomena that are occurring in the nature. How the objectives are optimized. Now, these non-traditional methods are also called meta-heuristics, and these are broadly classified into five categories: evolutionary algorithm, swarm intelligence algorithm, physics-based algorithm, human-based algorithm, and the rest. So, under evolutionary methods, the methods are genetic algorithm, genetic programming, evolutionary strategies, differential evolution, bacteria foraging optimization, artificial immune algorithm, biogeography based optimizer. They are all evolutionary based on biological evolution methods, phenomena. Then swarm. Swarm means group behavior. Swarm intelligence heuristics. The particle swarm optimization, just like birds flow, you have observed in the sky, birds always fly in a flock, in a group. Similarly, artificial bee colony and colony optimization, shuffle frog leaping algorithm, firefly algorithm, glowworm swarm optimization, cuckoo swarm. These are all swarm optimizations. Then physical phenomenon, the physical rule, the rule of physics, the simulated annealing that is based on your heat treatment process, the annealing process, gravitational locus search, Big Bang, Big Crunch, gravitational search algorithm, charge systems are like this. These are all physics-based optimization with the heuristics or non-traditional algorithm. These are some more physics-based heuristics. Then another category will be human behavior, based on human behavior. One is teaching learning based optimization, TLBO, suggested by one of our NIT professor of Surat, Professor R.V. Rao. He has also proposed Jaya algorithm. Then other algorithms are harmony search, taboo search, group search, imperialistic competitive algorithm, league championship algorithm, firework algorithm. How the in Diwali, just like you put firework, on that basis, the algorithm, how based on that behavior. These are some more algorithm which are human based. This slide shows. Then the last category is other heuristics. Invasive weed optimization, mimetic algorithm, monkey search, sapling growing algorithm. So these are just know the names. Where today's class is not meant to teach all these, this one. Just an overview I am giving you. What are the non-traditional optimization techniques? Now let us start our single variable optimization method. Let us start with the most fundamental method, that is analytical method for optimality, where you will get 100% accurate result. And it is always advisable that we will always try to solve it by this method. If not possible, then only we'll go to the numerical method. That is an approximate method. That is an iterative method. So this method can be stated like this. Optimal point is graphical representation of a solutions. So optimal point exists at some values of x if the first derivative of the objective function is equal to 0. So first we take the first derivative of the function, then we equal to 0 and solve it. And then we find out the values of x, and we can say that at x we will have the optimal solution. Now to know whether there is that value of fx, at this particular of x is maximum or minimum, we have to take the higher order derivative. So if n is the lowest order derivative that yields a non-zero value at x, means we will keep on taking the higher order derivative, second derivative will take and check at that values of x if we will find a non-zero value. If you don't, if it's still zero, we'll go to the third order derivative and check. If the value is still zero, we'll go to the fourth order. So like this, we'll start from second order and we'll go on increasing it till we find the first non-zero value of that derivative. Once we find a non-zero value, we stop it there and we note down what is that order of derivative at which we get for the first time a non-zero value. Then this x will be point of inflection if that value of n is odd. But if that value of n is even, we'll get a local optimal solutions. And this local optimum will be either maximum or minimum. So this local optimum will be minimum if that on nth order derivative at that x is a positive value. If it is positive, it is a minimum point. But if that nth order derivative is negative, it is a maximum point. So this is the analytical procedure by which we can find out all the point at which we'll get the optimal solution. And these optimal solutions can be classified into two categories, either point of inflection or local optimum solutions. And this local optimum can be either of two types, either minimum or maximum. So this should be clear through if we solve an example. Let us take the very simple example. Identify the local maximum and local minimum and point of inflection for these objective functions. So this is a unconstrained optimization problem. Unconstrained. We are not specifying any constraints here. We are only specifying only the objective function, the top line. F of x is objective function that is equal to x to the 5 minus 4x4 plus 3x3 plus 2. Now tell me at what values of x the f will be maximum and at what values of x f will be minimum, or at what value of x we will get a point of inflections. Can anyone tell me? You please recall your plus 2 knowledge and tell me. And also the procedure that I have told you just now. Apply that and you solve it and tell me. All of you, do have a pen and paper? Hello? Am I audible?
Yes, sir. Yes, sir.
No, you are only, yes, sir. What about the participants? How many participants are there? Hello?
Yes, sir. It's audible, sir.
No, at least one participant, please respond.
Audible,
Hello?
sir.
What is your name, please?
Sir.
What is your name?
Audible, sir.
Yeah.
Audible,
What is your
sir.
name? Please tell me. One.
Subhasis Swai.
Subhasis
Audible,
Swai.
sir.
Subhasis Swai, please solve this problem on a pen and paper and you tell me. All of you, please solve it and tell me. Unless you do it yourself, you'll not able to understand. Can you do it or no?
I'm trying, sir.
Please try. First, find your first derivative of f of x. And then what will you do? You equate to 0. Then solve it. So f of x will be, the first derivative will be x5 is 5x4. Then x4 is 4x3. So 4 into 4 will be 16. So minus 16x cube. Now x3, if you take derivative will be 3x square. So 3 into 3 is 9x square. And 2 will be 0. So this is the first derivative. And for optimality, the first derivative must be equal to 0. And then we'll solve it. So 5x4 minus 16x cube plus 9x square is equal to 0. So left hand side, we can take x square common. So we'll get 5x square minus 16x plus 9 is equal to 0. So left hand side is product of two factors. So that means x square is equal to 0 or the second factor, that is 5x square minus 16x plus 9 is equal to 0. When x square is equal to 0, if you solve it, you will get x is equal to 0. And when we solve 5x square minus 16x plus 9 is equal to 0. This is a quadratic equation. And in high school, we already know it. The solution of a quadratic equation, because maximum power of x is 2, the solution of a mathematical equation, the roots of an quadratic solution would be minus b plus or minus square root of b square minus 4ac divided by 2a. Do you remember this formula from high school?
Yes, sir. Yes, sir.
Okay. Now b is your second term, that is 16 minus b is minus 16. So minus b will be plus 16. Plus or minus square root of b square. So minus 16 square will be 16 square. Then minus 4ac. A is 5 and c is 9. So 4 into 5 into 9. Divided by 2 into a is 5. So 16 plus or minus, now under the square root will be 76. So when you solve it, you will get 2.472, or we'll get two values because it is a quadratic equation, or 0.728. When you take plus, you will get 2.472. When you take minus, you will get 0.728. So here we will have three roots of x, three values of x, that is 0, 2.472 and 0.728. At these three values of x, we will get the extreme values of x, objective function f of x, either maximum or minimum or point of inflection. To decide that, you have to now take the higher order derivative. So now let us take next higher order derivative, second derivative. So let us take second order derivative. So there are three optimal points, these three, 0, 2.472 and 0.728. So second order derivative will be 20x cube minus 48x square plus 18x. Am I correct?
Yes, sir.
And third order will be one order. So x3 will be 3x square. So 3 into 20 is 60. X square will be twice x. So 2 into 48 is 96. And 8x will be 1. So 18 into 1 is 18. We will now check for each values of x. X equal to 0, we will check. Then x equal to 2.472, we will check. X equal to 7. At third order of derivative, we will get for the first time a non-zero value. So let us first try it x equal to 0. Why you are doing this? There is some noise coming. Please mute it. Hello. Please mute it. All the participants, please mute this one. Somewhere there is a noise is coming. Yeah, thank you. So now let us check it x is equal to 0. The second order, what will be the value of when x is equal to 0? The second order derivative f double dash x. So x cube is 0, x square will be 0, and x will be 0. So the total value will be 0. So we will not stop here because we are not getting a non-zero value. So that's why at x equal to 0, you try the third order derivative. So let us put the third order derivative here. Let us put x equal to 0. So 60x square will be 0, 90x will be 0, and 18 will remain. So 18 we get for the first time a non-zero value. And when you get it at the third order derivative, that's why the value of small n will be 3. And since 3 is odd, we will write down that at x is equal to 0, we will get a point of inflection. Is it clear? Why it is point of inflection? Because we get for the first time a non-zero value, that is 18 at third order derivative, because at second order derivative we are getting a value 0, which is not non-zero. So n is equal to 3, which is odd. That's why this is a point of inflection. Now let us check for the second point. There is x is equal to 2.472. Put it here, the f double dash x, There is 20x cube minus 48x square plus 18x. Put x is equal to 2.472. Do you have a calculator? Otherwise, you open your mobile phone and calculate this f double dash x at x is equal to 2.472 and check if you are getting 53.3. Calculate 20 into 53.3 to the power 3 minus 48 into 53 point, not 53.3, sorry. At x is equal to 2.472. So 20 into 2.472 to the power cube minus 48 into 2.472 to the power 2 plus 18 into 2.472. And check whether you are getting 53.3 or no. Please respond if anybody has got it. Are you calculating?
Yes, sir.
Okay. Did you get 53.3? Let me switch on my fan. Sorry. Did you get 53.3? Hello, anyone? Hello.
Yes, sir.
Got it, na? Okay. So, will you go for the higher order derivative? Yes or no? Just like for x equal to 0, we found out the third order derivative, we got 18. Should we also calculate for third order derivative here?
No,
No
sir.
need, sir.
No, because no need. Because already we got a non-zero value, that is 53.3. And at what order of derivative we got this non-zero value? That is second order derivative. That's why n is equal to 2. Since n is equal to 2 and it is even, so this value, at this value, we will get either minimum or maximum. Why will it will be a minimum value? Because this non-zero value, which is 53.3, is a positive. Since it is positive, the value of f at x is equal to 2.472 will be a minimum values. Understood? Now let us try for the third solution. That is x is equal to 0.728. So when you put x is equal to 0.728 at this second order derivative, there is 20 into 0.728 to the power 3 minus 48 into 0.728 square plus 18 into 0.728. You check, you will be getting a value that is minus 4.6, and this is not equal to 0. So we stop here, and this we get it at second order derivative. That's why here also n is equal to 2, and this is even. And since this non-zero value, that is minus 4.6, is a negative value, the objective function f of x will be maximum, local maximum at x is equal to 0.728. So thus, at these 3 points, we get 3 different type of results. At x is equal to 0, we get point of inflation. At x is equal to 2.472, we get local minimum. At x is equal to 0.728, we get local maximum. And this result that whatever we get is 100% accurate result. Now you solve another example, you try yourself. Can you solve it? Same procedure. So first find out first derivative. So 3x4 will be 4x cube. So 4 into 3, 12x cube. Then x cube here will be 3x square. So 3 into 24 is 72 x square. Then this x square will be twice x. So 2 into 66 is 132x. And 72x will be 72. So first derivative you equate to 0. Then solve it. When you solve it and factorize it, you try it yourself. You keep on factorizing it by this. And finally, you will get a very simplified form on the left hand side. Is x minus 3 into x minus 2 into x minus 1. This factorization you have already learned in your high school level course. So thus, when x1 minus 3 is equal to 0, we get x is equal to 3. Similarly, x minus 2 is equal to 0 means x is equal to 2. And when x minus 1 is equal to 0, you get x equal to 1. So we get 3 solutions for x. 1, 2, 3. Now we have to decide at this 1, 2, and 3, what is the type of objective function we will get it, whether maximum, minimum, or local point of inflection. So to do that, we have to find out, we will take the higher order derivative. So let us find out, no, sorry, if you are using MATLAB, the solution, this x equal to 1, 2, 3, can be very easily find out by using the command called roots. That is called finding the roots of an equation. The first derivative is this one, is equal to 0, and we have factorized it manually and we got the solutions. So to use the MATLAB, you have to first write down the coefficients of the x, the power of x in a descending order. So here highest power of x is 3, that is x cube, and its coefficient is 1. So first write down 1. Next will be x square, this x square. So its coefficient is minus 6. So next you write down minus 6. From x square, next down will be x to the 1, and its coefficient is 11. So write down plus 11. Then x1, the next will be x to the power 0, that is 1. So 1, its coefficient is 6, minus 6. So write down minus 6. So this you write down in a matrix and equate to x. So x is an array or matrix where the elements are 1, then you put a blank or comma, then write down minus 6, then blank plus 11, then blank minus 6, and we enclose it with the square bracket. So if you write down like this and enter in MATLAB, MATLAB will understand that this 1 minus 6, 11 minus 6 is a matrix of 1 row and 4 column, and it has been stored in a matrix named X. And in MATLAB, unless otherwise specified, every variable is an array. So this is an array. Then in MATLAB, the command prompt is 2 greater than symbol. 2 greater than symbol. In that, whatever you write down, this is a command prompt. And here you write down roots, R-O-O-T. This is a command. Then square bracket, and then write down whose roots you have to find out. So this X, define it. Then bracket close. If you press enter, you will get the solution. That is 1, 2, 3. Means x is equal to 1, x is equal to 2, x is equal to 3. At these values, this x square minus 6x square plus 11x minus 6 will be equal to 0. Either you find out the solution of an equations manually by factorizing it, or you can use the computer, and if you are using MATLAB, use the function roots and solve this equations. Find out the roots. Okay. So first derivative is coming back to the same problem. First derivative is this. Then second derivative will be x cube is 3x square. So 3 into 12 is 16. 36 x square. X square is twice x. So 2 into 72 is 144 x. Then 132x will be 132 and 72 will be 0. So we have three roots. Let us try at x equal to 1. What is the nature of optimality? So at x is equal to 1, let us find out the second order derivative value. So this is second order derivative. So here if you put x equal to 1, so 1 square will be 1. So 36 into 1 will be 36 minus 144 into 1 plus 132. So if you solve it, the values will be plus 24. So since 24 is non-zero, we stop it here. And we are getting the non-zero value, this 24, at the second order derivative. So n will be equal to 2. That is even. Even means either it is a maximum or minimum. Since this non-zero value, there is 24 is a positive value. So this f of x will be minimum at x is equal to 1. Understood? Similarly, let us try for x equal to 2. You try and tell me. First you try. At x equal to 2, what will be? Whether it will be minimum, maximum or local optimum? Sorry, point of inflection. Find out at x equal to 2, what is the value of the second order derivative? This 36x square at this, put x equal to 2 and solve it. And tell me the value. Are you calculating it? Please mute it.
X is equal to 1, function gives us the minimum value, x is equal to 3 minimum, x is equal to 2 maximum.
Very good, very good. Let us check it. What is your name? Hello?
Afsha, but
Hello?
Afsha, sir.
Yeah, congratulations. So please check at x equal to 2, the double derivative. Did you get minus 12 there? Upsir?
Yes, sir. It's 12.
Yeah. So this is non-zero.
Yes,
so we
sir.
stop it here. So n is equal to 2. Since it is even, either maximum or minimum. So minus 12 is a negative value. So f of x will be local maximum. Very good. And at x equal to 3, the second order value, second order derivative will be plus 24. Again, it is non-zero. So we stop here. N is equal to 2. Since plus 24 is positive value, so here we write down that f of x is local minimum at x is equal to 3. So thus, here we will get two local minimum, that is at x is equal to 1 and at x is equal to 3, and one local maximum, that is x is equal to 2. So this is the way we find out the optimal solution for a unconstrained optimization problem. And this is an analytical method. Date kete 13. Today's date 14. So तुम कौन है alternative medicine? Yes. तो 13th रे कौन तुम्हारी ये लगी? वो ही थी और 18 नो. अच्छा. 26 डेटा एनक्लोज करिया पड़ेगा. खाली ऑफिस रे दे दो. हाँ. स्टेपल मारिबा. ओके. एबे खोला न तो. एबे बंद है 6 बजलन ना. So that local minimum, any function you see it here. So here the bottommost point is called local minimum. And if the function is like this, the topmost point it is called local maximum. And if the combination of both this one means half you take from here like this, that is from here to here, and half you take from the other half like this, from here to here. So then this point will be called neither minimum nor maximum. We call it point of inflection. It is both convex and concave. Then a function may have many local maximum like this. There are three local maximum. Locally, it is maximum point, and out of which the most maximum is this. So this is called global maximum. Similarly, here we have three local minimum, this, and out of which most minimum is this. So this will be called global minimum. And in any optimization problem, our objective is to find out the global maximum and global minimum in the entire search space. And this traditional numerical method are not that much efficient to find out the global maximum or global minimum. It is with the use of non-traditional method like genetic algorithm, simulated annealing, that will help us to find out the global maximum or global minimum. So now let us learn, these are the examples of traditional methods. That is analytical method, 100% accurate, but we may not get all the time so simple problems where we can take the derivative. So in that case, we have to now solve it by numerical methods, approximate method. So for single variable optimization method, broadly it can be classified into two types of method. One is direct search method. There we need not have to find out any gradient or the derivative. And another numerical method where we'll be taking the help of the derivative. So these are called gradient based method. So under direct search method, we just find out the function value f of x, and then we'll compare, and we eliminate a portion of this region and find out finally the zone where the optimal solution will be existing. So under that there are 5 methods: exhaustive search method, bounding fetch method. Here using any of these two methods we'll find out, reduce the search domain to a smaller interval, and then the last 3 method, any of the method you can select, and then we can fine tune it, and finally we can tell with some precision that optimal solution will be presenting in a very small interval. It will not give you a points estimate, exact one value will not give, it will give you some range of values. You can because it is not 100% accurate result. It is an approximate value. We can say on an average, it will lie, the optimal solution will lie from this point to that point. So it will be interval estimate. Gradient based method, we have Newton-Raphson method. This will give you point estimate, one value we will give it. Then bisection method, second method, and cubic search method. This will give you interval estimate, a range of values. Then in multivariable optimization method, also these are classified into 2 categories: gradient based method that deals with the derivatives. So there we have 3 methods: Cauchy's steepest descent method, Newton's method, and Marquardt method. And direct search method, there no derivative is to be found out, only values of function, and then compare. We'll have simplex search method, Hook-Gibbs pattern search method, Powell's conjugate Datsun method. In today's class, we will learn this Hook-Gibbs pattern search method. And here we learn Cauchy's steepest descent method. And then here one method we will discuss, the exhaustive search method, and from here one method we will select, one from first 2 and one from the these 3, and one from gradient based method, depending upon the time availability. Okay. Now, whatever the methods that we listed down, that is all for unconstrained optimization problem, when there are no constraints. But when there are constraints are associated, then the methods are penalty function method, method of multipliers, variable elimination method, complex search method, random search, rank one method. Now let us discuss the single variable optimization problem, the numerical method. And it is first let us discuss unconstrained, then we will discuss the constraint method. So minimum point is found in 2 stages. In first stage, we will find out a bracket or an interval that is defined by lower bound and upper bound that contains the minimum point. So these are called bracketing methods. And these bracketing methods are these two. And the second measure, depending on the desired accuracies, we start from this bracket, whatever we will get from using the first stage, then we will improve upon and further reduce the region till we get the optimal solutions. Interval will be much less the interval, better the accuracies. Instead of telling that solution lies from minus infinity to plus infinity anywhere, then you can say there is blindly anyone can say that solution exists from minus infinity to plus infinity. Then further, as and when as much as this region is reduced less and less, the accuracy of the result is higher and higher. And finally, if you are able to reduce to one value, is a 100% accurate. But if you say that the solution lies from 2.1 to 2.2, some region. So depending, so this is we are expressing the solution in terms of a interval estimate. The solution lies from 2.1 to 2.2. But if you say the solution is actually 2.15, then this is 100% accurate result. Okay. In bracketing method, which we use in the first stage initially, we have two methods. One is exhaustive search method and bounding fetch method. Any one of the method can be used in the first stage. This exhaustive search method is also called equal interval search method. At equal interval, you go on, find out the value of f of x, we compare, and then we declare that in this interval, the solution will lie. Let us discuss now exhaustive search method. This is the simplest method. Here, what do you do? The initial search interval u to v, that lower bound and upper bound, no, this will first take. And then we divide this interval into n equal parts. Here this is u to v, this is search domain, lower bound and upper bound. We divide it into equal parts. Let's say if n is equal to 4, we divide it 4 equal parts. Then at each and every point, starting from the u, we find out the value of f of x. And then we compare. And then based on this, whether it is less or more, we'll take a decision there in which region the solution lies. So, number of these three are intermediate points, and these u and v are the exterior point, boundary point. So, if n is equal to 4, we'll have three intermediate points, this, and this. So, in general, you can say n minus 1 intermediate points. And there will be always two boundary points at u and the v. So, the total number of points will be n plus 1. That is 4 plus 1 is equal to 5. 1, 2, 3, 4, 5. At this 5 point, we have to find out the value of f. So total search point will be 5, n plus 1. Intermediate point, n minus 1. Now, each interval, we have divided into here 4 interval. Each sub-interval, u to v interval, and from each of these 4 interval, the width will be how much? So total is v minus u, then divided by 4, and that is n. So in general, the width of each sub-interval will be v minus u divided by n. So we start from u, and then at each and every search point, we find out the f of x. So here, we will be finding out the values of f at equally spaced point. That's why it is also called as equal interval search method. And here we search begins from the lower bound, that is x is equal to u. And then we proceed towards the upper bound, that is v. From u to v, we will proceed. See here, this is u and this is v. This is a total interval. And these were divided into an equal number of intervals. At any time, we will compare 3 consecutive points. Let's take 3 consecutive points, x1, x2 and x3. And at x1, find out the value of f of x. Let's say it is f of x1, there is f1. From here to here, the height is f1. And at x equal to x2, find out f of x, there is f2. So from here to here is f2. And at x3, the value of f of x is f3. Now this f1, f2, f3, let us compare. And here, as x value increases, f value is reducing. And since our objective is to find out the minimum value, locate the minimum value of f. So this graph is f of x, and here the minimum value exists here. We start from u here, and as we are proceeding from u to here, at each and every point we are calculating the value of f of x, and we observe that three consecutive points x1, x2, x3, the f values is decreasing. So we are more and more happy. It means we are proceeding towards lower and lower values. So decision would be, let us proceed further. That means let us find out the f at the next point, at these points. So long as we get like this, f1 is greater than f2, then greater than f3, at the three consecutive point, the search proceeds in the forward directions. The moment f of x value starts increasing, we stop it there, because here once you exceed this bottommost point, the value of f goes on increasing. So we should stop here. The moment it starts increasing, we should stop here. So here you see these are three consecutive points. So f1 is greater than f2, but f3 is greater now. F3 is not less than f2. So here it is not f1 is greater than f2 greater than f3. So here the values of f starts increasing. At the three consecutive points, we observe that f values has started increasing. So we stop here and declare that this minimum point lies between this x1 to x3. Here, of course, if you see closely, this bottommost point lies between x2 to x3. But this may not be all the case, all the time. That's why to in a safer side, we have to write down that the minimum point lies from x1 to x3. Take three consecutive points, x1, x2, x3. So write down from x1 to x3. Let us see other cases. So this is not the case always from x2 to x3. Why? Let us see this case. This is three consecutive points, x1, x2, and x3. Here, x increase from x1 to x2, f of x decreasing, means f2 is less than f1. But comparing x2 to x3, f value is more, means f3 has started, f has started increasing. f3 is not less than f2, although x3 is less than, greater than x2. So here f value started increasing, and here bottommost point is here, x minimum. Here f value is minimum, and here x minimum lies from x1 to x2, not between x2 to x3. But in earlier case, minimum point was lying between x2 to x3 for the same condition. That is, f1, f2 is less than f1. Sorry, f2 is less than f1, but f3 is not less than f2. So f2 is less than f3, and also f2 is less than f1. So in such cases, in both the diagram, in one case, minimum point lies between x1 to x2. In other case, it lies between x2 to x3. So to be on the safer side, take the union of both the cases. So write down x minimum will anyhow realize from x1 to x3. In this case, you see, here x minimum lies from x2 to x3. Same condition, f2 is less than f1, f2 is less than f3. Although x value is increasing, but f value is not decreasing monotonically. It has started, initially it started decreasing, then it started increasing. Means we have crossed this minimum point. So taking the intersections, case 1 is x1 to x2, case 2 is x2 to x3. Taking the union of both these cases, combining both the cases, we can write down x minimum lies between x1 to x3. So we started from u to v, now we've reduced to x1 to x3. This is the bracket. This is exhaustive method. So the algorithm would be like this. First, initialization. So first we assume the initial search interval, the value of u and v. Then how many times you are going to divide it equally, that is n. Then calculate the width of subinterval, that is small d is equal to v minus u divided by n. Then you start the first point, x1. We will take three consecutive points. So you start the first point from u, the lower bound. So x1 is equal to u. The next consecutive point is x2, that will be x1 plus d. The next consecutive point is x3, that is x2 plus d. Then find out the values of objective function. F of x1 is f1, f of x2 is f2, f of x3 is f3. And here let us compare. If f2 is less than or equal to f1 and also less than or equal to f2, means f value has initially decreases and then it is increases. If this condition is satisfied, then we stop it. And we print that minimum values lies between x1 to x3 and we stop it. So this is the step-by-step procedure. Otherwise, you repeat to the next consecutive points, you take it. So the x2 will be x1, x3 will be x2, and x3 will be the new point, that is x2 plus d. And again, we start finding f of x1, f of x2, x3, and continue till we get this logic, get it, this condition is satisfied. Till we reach to the end point, that is v, that the x3 is less than or equal to v, we keep on doing it, go to step 3. Otherwise, declare that we have searched the total search space from u to v, but you did not get any minimum point. So x minimum does not lie in u to v, or maybe that boundary point x minimum may be u or v, and then we stop it. This is the algorithm of exhaustive search method, numerical methods. See here, the u and v has been so selected initially that because initial assumption of search domain for x, u, v is very, very important for this exhaustive search method. And here we have so selected u, v that the minimum point does not lie in u to v. So here we start from u, we keep on searching it all the time, it is less than, less than, less than. So we keep on searching it and you reach at extreme point, but still the value is not yet started increasing. So you will declare that x minimum does not lie in u to v. Or maybe like this, see here minimum point lies on the boundary point. So here we start at from u and you keep on searching it all the time, value is increasing. So once the value started increasing, we stop it there. But we cannot say that minimum lies from x1 to x3. Here the minimum point lies at the boundary point u. And if this is the case, boundary point, the minimum point lies at the boundary point x is equal to v. Various possibilities. Okay, now let us solve an example. So minimize f of x is equal to x square plus 16y. This is a single variable problem, only one unknown variable, that is x. And here it is a unconstrained problem because there are no constraints specified here. So we have to use exhaustive search method, and initial search page is 0.1 to 5.1, and we have to divide it 10 equal divisions. Let us solve it. So here let us identify the lower bound u is equal to 0.1 initial search space, and upper bound v is equal to 5.1, that is given in the problem. And small n, there is a number of equal division is equal to 10. So what is the next step now? Find out the width of subinterval. So small d will be equal to v minus u divided by n. V is 5.1 minus u is 0.1 divided by n is 10. So it will be 0.5. So let us begin from u. So x1 is equal to u and u is 0.1. x2 will be equal to next point, that is x1 plus d. x1 is 0.1, d is 0.5. So we'll get 0.1 plus 0.5 is 0.6. And x3 is next point, that is x2 plus d. So 0.6 plus 0.5 will be 1.1. At these 3 points now, we'll find out the value of f of x. So f of x is x square plus 16 by x. So at x is equal to 0.1. So 0.1 square plus 16 by 0.1 will be 160.01. And at x2 is equal to 0.6, the value of f will be 27.027. At x3, there is 1.1, it will be 15.755. And if you compare that, the values are decreasing gradually. 160 is greater than 27, 27 is greater than 27. So 15 is less than 27, 27 is less than 160. So value is decreasing. So what is your conclusion? Don't stop, proceed to the next point. So in that case, this x2 will be x1. So 0.6 will be x1, 1.1 will be x2, and 1.1 plus 0.5, there is 1.6 will be x3. So this already have calculated. We just substitute it. Only at 1.6 will calculate. So this is all. So value is not value. F value is not yet started rising. So we have to continue. It is decreasing. So now x1 will be equal to x2. There is 0.6. x2 is equal to x3. There is 1.1, and x3 will be equal to 1.1 plus 0.5, 1.6. So let us see. So f1 at 0.6 already have calculated earlier. So just write down 27.027. 1.1 already have calculated earlier, 15.755. Only at 1.6 you calculate. So 1.6 square plus 16 by 1.6, it will be 12.56. Again, if you compare these three value, it is still decreasing. That is 27 is greater than 15, 15 is greater than 12. So continue. So like this, if you continue, let us tabulate now. At 0.1, it is 160.01. The next point, 0.6, it is 27, less. So let us check at the next point. 1.1, it is 15, less than 27, previous values. Then 1.1 plus 0.5, 1.6. At 1.6, f of x is 12.5, which is less than 15.7. So continue. 1.6 plus 0.5, it is 2.1. At 2.1, value f of x is 12.0, less than 12.5, still continue. 2.1 plus 0.5, it is 2.6. At 2.6, it is 12.9. For the first time, now we observe, it is not less than the previous value. So 12.9 is not less than 12.029. So we stop here. We observe that value has started increasing. Already we have crossed the minimum point. And then we'll write down our answer. So now the last three consecutive point is what? 1.6, 2.1 and 2.6. So this 2.6 is x3 and 1.6 is x1. So we'll write down that minimum point, that x minimum will lie from x1 to x3. There is 1.6 to 2.6. This is the answer of this problem using exhaustive search method. Here the result is not one value. It says that any value lying between 1.6 to 0.6 are feasible solution, and in this the minimum point is lying. So we are not 100% confident that at what one particular value x f of x is minimum. Here we say a range of values. So that's why it is not 100% accurate result. And this interval, if it is less and less, we say result the result is more and more accurate. So this, if you can further reduce this interval, then we can say that the result is more accurate than this. So we'll use another method in second stage, starting from this interval, and we'll further reduce it. So the same example that this one, if you also solve analytically, you will find out, like, because it's a simple problem, we can also solve it analytically and you can check it. So let us first derivative. So first derivative will be x square is 2x, 16 by x, 1 by x will be minus 1 by x square, then equal to 0. When you solve it, 2x into x square is twice x cube, minus 16 divided by x square is 0. So that means 2x cube, x square into 0 is 0, doing cross multiplication. So 2x cube minus 16 is 0. There is 2x cube is 16. So x cube is 16, 8. So x will be 2. So only we have one value, that is x equal to 2. So this is the x equal to 2, and also we obtain that instead of telling x equal to 2, this is because it is 100% accurate result. We can say accurately that f of x will be minimum at x is equal to 2. And of course, we can also tell with 100% confidence that it will be minimum, not maximum. So to do that, take the higher order derivative, that is second order derivative. So if f of x is x square and first derivative is 2x, then 2x if you take derivative will be 2. And 16 by x square, if you take it, it will be 32 by x cube, negative or negative is positive. Now at x is equal to 2, substitute the value here, x equal to 2. So 2 plus 32 by x cube. So 2 to the power cube is 8. So 32 by 8 will be 4. 4 plus 2 will be 6. This is a non-zero number. So we stop it here. And at second order derivative, we are getting the first time a non-zero value. So we stop here. No need to take third order derivative. And since this non-zero value is positive, f of x will be minimum at x is equal to 2. So we are sure that it is minimum point, and it occurs at x equal to 2, and this is 100% accurate result. And numerically, when you try to solve the exhaustive method also, you see the 2 lies between 1.6 to 2.6. We are not able to say confidently that it is at 2. We say it is somewhere between 1.6 to 2.6. If you could have told that it is between 1.9 to 2.1, then that result will be much more accurate than this 1.6 to 2.6. That means if this interval width is less and less, the accuracy of the result will be more and more. Am I clear? So this is all about your exhaustive search method. Now suppose the same thing we want to improve the accuracies. So in that case, you have to divide this interval by more number of division. So that time we are taking 10 equal division. Now if you divide it by 5,000 times, the width of interval will be less and less, and your accuracy will be more and more. If you observe carefully here, this width of interval is how much? 2.6 minus 1.6 is how much? 1. This 1 means what? 2 into 0.5. And 0.5 is here width of the interval, d. That means this width of interval is twice d, where d is width of subinterval. Here you see the step size is 0.5, 0.1, then 0.6. So width is, the step size is 0.5. Then 0.6, next step is, next value is 1.1. So 0.6 plus 0.5 is 1.1. So the width is 2d. So this width can be reduced. It is a function of d. So if d value is less and less, this 2d will be less and less. That means this interval will be less and less. Means the accuracy will be more and more. So if number of division is more and more, accuracy will be more and more. The width will be less and less. But 5,000 times calculations doing this and reaching to the optimal point will be very, very time consuming, and by hand calculation it will be impossible. You have to use the help of computer program. So this algorithm for exhaustive search method we can write down using a MATLAB program or C program or Patel program, whatever you are convenient with. So MATLAB program for this exhaustive search method will go like this. In MATLAB, any command starting with percentage symbol is a command line. So they are all command line. So first thing is what? You will write down, you have to read the values. So read command is input in MATLAB. So write down input, within bracket, write down the command statement. So within these two apostrophe, whatever you write down, that will be displayed on the screen. So and the pointer will blink there, and it will be waiting for the some number to be fed by the u. So whatever number will fed it, that will be stored in the variable called u here, this u. Similarly, enter the upper bound of search space v is equal to, then whatever value will feed it, it will be stored in the variable called v. Similarly, enter the number of equal division n is equal to, that number will be stored in n. So these are all the three read command. Then we'll define, this is a global variable, NF is a global variable. In MATLAB, capital letter is used for global variable. So main program and there will be subroutine program. So this global variable will be effective both in main program as well as in the subroutine program. So usually this NF we are using to track that how many times the function have been evaluated. So initially we'll write NF 0 and as and when the subroutine, in the subroutine we'll write down the function f of x. As many times the subroutine is called for means that many times function is evaluated. And that time NF will be incrementing by 1. So we will keep a counter of n, and when the program ends, whatever was the value of NF, it will give that this many times function has been evaluated. If we want to keep track of number of iterations, we can initialize k equal to 0. So first write down the width of the interval d. So d is equal to v minus u divided by n. In MATLAB, since every variable is treated as a matrix, so unless we write down a point before a division or a multiplication, it will not treat it as a simple division or multiplication. It will treat as a matrix division. But we want a simple division here. That's why you have to put a dot before a division here. It is a just mathematical division, not the matrix division, right? So a dot has to be put always before a division mark. This rule is also applicable for a multiplication symbol. Then what you do, x1 is equal to u. You already have read it, that value, that is substitute for x1. Then x2 is equal to x1 plus d. Then x3 is equal to x2 plus d. Since here I have written 3 commands in one line, and this one I have separated with a semicolon. If you use semicolon, the result of that command will not be displayed on the screen. This will be hidden. More and more, if you display it on the screen, means the computer program will be slowed down, right? So unless another way is required, don't display at every step the result of your command. Okay. Then here you write down f of x1. So this is, we are sending the control command to a subroutine f.m. And main program, the file name we have given what? Adjust.m is the main file name. And function file name or subroutine file name is f.m. Here in MATLAB, every file have a extension .m, m for MATLAB. Both for main file as well as for the function file, the extension should be .m. So when you are writing f of within bracket x means we are calling that function file f.m. So f of x1 we store it in f1. Similarly, f of x2 store it in f2, f of x3 in f3. That means we are computing f1, f2, f3. This percentage symbol, if you write at the beginning, entire line is a comment. But if this percentage symbol is put in between a line, the single line, means whatever is there in that line after subsequent to this percent symbol, from here to here, it is treated as a command. Means computer will just ignore from here till the end of the line. It will compute only up to this point in this line, and rest it will just ignore. So then we'll use the do while. Yes. Any problem? Hello? I am hearing some noise here. Ting, ting. Anyway, let us continue. So then we will use the do while command. So long as x3 is less than or equal to the upper bound v. Here in MATLAB, less than or equal to is like this. We have to use the symbol. F printf. Hello, am I audible?
Yes, sir.
Yes,
Yeah.
sir. Yes, sir.
Okay,
You are
okay,
audible.
okay. Okay. Yeah. This fprintf is the output command on the MATLAB. This is similar to your C program. So here, whatever you write down inside this bracket will be displayed. And here, within this apostrophe, from here to here, whatever is this is a format you specify. Put a command, and from here, all the variable name you have to write down serially, whose value we are going to print out. So first value will be x1, then next value we are printing is f1, then x2, then f2, then x3. 6 variable value we are going to print it out. And we have to specify this format in this. From here to here, we are specifying the format. See here. So f, it will just write down at f, then this bracket will write down. The moment it will find out a percentage symbol, means this is specifying that this is the format. That is 0.3f means with 3 decimal place, this fraction value format will be displayed. So percentage 0.3f, in this space, the value of x1 will be printed. Then bracket close will be printed, then equal to, then percentage 0.3f in this place, the value of next variable f1 will be printed. Then comma will be printed. Then slash t means a space, a tab space will be given. Then f bracket open will be printed. Then in place of percentage 0.3f, the next value, that x2 will be printed. Like this, f of x2 is equal to the value of f2 will be printed here. Then a tab space, then f of x3 will be printed. Then this 0.3f will be, the f3 value will be printed. So see here, the 6 variable, 3 percentage symbols should be there. 1, 2, 3, 4, 5, and here also it will be 6. There is a mistake here, it should be percentage 0.3f. Let me correct this.
The slash t, why we are writing, sir?
Here. Hello, not response. Please tell me what is the problem. Hello.
Slash t, we are writing why, sir?
Slash t is to provide a tab space. Some space we are putting it in, just to differentiate. Space, some.
Okay.
And amount of tab in a keyboard, there is a tab button is there, na? When you place that tab, it will some 3 to 4 blank space will be given. So that is the result. Tab, tab. Where did I go? Here there is mistake. So here it should be percentage. Okay. Oh, because of that it was. So here there should be percentage. So 6 variable, 6 percentage. Okay. Then if f1 is greater than or equal to f2, and this is end condition. In MATLAB, if you give 2 ampersand means this is end condition. Then f2 is less than or equal to f3 means we have to stop it here. Before stopping it, you have to write down the result. Fprintf, minimum point lies in the interval, some x1 to x3. So this is the 2 format we are giving. Then the slash n means new line character. We will go to the next line. And then x1 value is printed here, first here, and then comma, this x3 value will be printed here. Then fprintf, number of iteration is percentage d. This is an integer value. F is a fraction value, d is an integer value. So this k value, number of, whatever the value of k at that time, it will be printed here. Similarly, number of function evaluations, whatever the value of nf was there, it will be printed here. So this nf or k is the integer value. That's why the format is percentage d, and then return. So this is the computer program. You can find out in my book. The same program is available, or also in video lecture also I have explained it. You can see all this computer program and try it, and you can find the solution of any exhaustive search method using this MATLAB program. Else, you are not getting, you have to continue. That's why x1 is equal to x2, x2 is equal to x3, x3 is equal to x2 plus t, and again you find out this function value. Here, since already you have f2, so you are just substituting it. F3 is substituting it. Only f3 value you have to calculate afresh. So you call for this subroutine f. K is equal to k plus 1. One iteration is over. That's why you are updating the value of k. K is equal to k plus 1. This end is for this end if condition is. This end is for the while loop. Here for this if condition one end, for this while condition one end. So two end condition is here. Otherwise, if you don't get any result, it should be if x is equal to greater than v, write down that minimum point does not lie in this u to v, or minimum point can be either at u or v. Now this should be the content. That was the content of exhaust.m, whatever is there. But function file, this is the content of f.m. You have to write down first word should be function. In any function file, the first word should be function. If it is not function, it will be treated as a main file. So function, then square bracket open, square bracket close, y is equal to f of x. If file name is f.m, this must be f. If file name is abc.m, here you should write abc within bracket x. Then this all you written. Then write down this function. What is that function you are going to calculate? So y is equal to x square plus 16 by x. So x square is nothing but x into x. So x in my computer program multiplication is star into x. Since it is multiplication in MATLAB, it has to be preceded by a dot. Otherwise, it will be treated as a matrix multiplication plus 16 divided by x. So here also since a division preceded by dot. And then we write down, since we are calling this function, when as and when it is called, the value of nf is to be incremented by 1. Just to keep a track that how many times you are doing the f of x calculation. And last time may be written, even if you don't write, it will be understood. So this is the content of a function file to calculate the function value f of x, and the previous 2 slides or 3 slides were the content of the main program. And in the command prompt, if you write the adjust and press enter, you will get the result. It will ask for you put that value, v some value, and some value, will get the final result. Now let us consider the second stage of optimization. So we start whatever you get the interval from the first stage, that is exhaustive search method, then we improve the solution. And in second stage, either you use region elimination method or gradient based method. In region elimination method, you don't calculate any derivative. You have to calculate only the value of objective function and compare and eliminate a portion of the interval and reduce it. But in gradient based, you have to find out the value of f derivative. In region elimination, we have these 4 methods: interval hopping method, Fibonacci search method, golden section search method, and point estimation method. And in gradient based method, we have Newton-Raphson method, bisection method, secant method, cubic search method. Now let us first understand the principle of region elimination. See here this is a f of x, and minimum point lies here, and the search domain is u to v. In the search domain, let us take any 2 intermediate points, x1 and x2. At x1, the value of f is from here to here, that is f1. At x2, from here to here, this is value of f2. And here, the hx increases, the value of f decreases, right? So here, we start from the lower value, from here. And we proceed towards the higher value f1. And further, if you proceed like this, then f value start increasing. But our objective is to find out the minimum value. So that's why we can say with 100% confidence that if you proceed further, we will not get the minimum value because f value has started increasing. So that's why confidently we can eliminate this region. Am I clear? I repeat, take any two intermediate points in the search interval u to v. At these 2 points, find out the value of f of x. So f of x1 is f1 from here to here. F of x2 is f2. Then we compare f1 and f2. One will be higher, one other will be lower. So select the lower value. So this is a lower point. From lower point, you move towards the higher point. And further, if you want in the same direction, we are moving from right to left. So from here, we have started coming here. And further, if you move, f value started increasing. That means minimum point will never lie beyond this point. So eliminate this region. So eliminate left of x1. Let's say this case, x1 and x2. At x1 value is less, f1 is less. But at x2 value is f2, which is more. So move from lower value to higher value. So from here, let us move to here value. So we are moving towards right. Beyond this, still increasing. So you can delete right of x2. So if f2 is greater than f1, delete right of x2. If f1 is greater than f2, delete left of x1. And if both are equal, if f1 or f2 are equal, because you take any two values, there may be three cases. Either it will be less or greater or it is equal. If it is equal to, the from here to here also value increases, from here to here also value increases. So right of x2 you eliminate, left of x1 you eliminate. So you can say the minimum point will lie from x1 to x2. So these are the three principles of region elimination. So those three principles has been written down here. Take any 2 points, x1, x2, in the interval u to v. There is between x and x2 is, let's say, greater than x1. Mean x value increases from x1 to x2. At x1 and x2, find out the f of values. If f of x1 is greater than f of x2, delete left of x1. If f of x1 is less than f of x2, delete right of x2. If both are equal, delete left of x1 and right of x2. Now let us discuss one such method, how we can able to reduce the result whatever we get from the bracketing method, that is in the first stage, that is exhaustive search method, further less, and we can get a result with a more accuracies. So in golden section search method, other methods can be Fibonacci search method or interval lapping method. Let us discuss only one because the time constraint. Other methods you can see from my video lectures. So initial search space U to V is whatever we have get it from the first stage, that is exhaustive search method. You have to linearly map to 0 to 1. And then we have to take two intermediate points in region elimination method. And these intermediate points are equidistant from both both the extreme points U and V. And this distance, let's say, becomes is tau. So x1 will be what? U plus t, lower value plus t will be one intermediate point, and the x2 will be from rightmost point minus tau. And then this one of the portion, the region that we eliminated by this method will be 1 minus tau times the width of the space at the previous iterations will be eliminated. And here we need not calculate the function value at both the points. Only one of the value will be repetition of the previous values. So at every iteration we will calculate only one new function evaluations. and less the number of function evaluation you get the result, means that program algorithm is more and more efficient. What is the value of tau? That will select such that every time one of the values will be same as the previous values, intermediate points. So that is, if you solve this 1 by tau is equal to tau square, the tau value will be 0.618. It is a quadratic equation, 0.618. So this is that golden number. And negative value is not considered. So 1 minus tau times it will be eliminated. So at every iterations, 1 minus tau, 1 minus 0.618 is 0.38.
Hello.
Sir is not audible as well as the presentation has also gone back.
Unable to hear.
Organizer ma'am, sir has left the meeting it seems. Can you kindly please check?
I'm trying to connect with the speaker. Please wait for 5-10 minutes. Maybe disconnected. I request all to wait for 5-10 minutes.
Everyone, please wait for 10 minutes. Like organizers are figuring it out.
The sir is joining within 2 minutes. Please wait. He is connected. Okay, ma'am.
Hello. Am I audible now?
Yes, sir.
Thank you.
Screen, sir.
Thank you,
Okay,
Bishim.
sir. Thank you.
You have reminded me that I was not able to
Okay,
know.
sir. Thank you, sir.
Moreover, I have
Okay.
put my mobile on silent mode. That's why I could not know.
Okay, sir.
Okay, so where are we now? So again, I have to upload now. Entire screen. Select. Select the entire screen. Okay. Hello. Is my screen visible now?
Yes, sir. Yes,
Yes,
sir.
sir.
It is visible.
Acha, now tell me where did I get this one?
Is one of the participants please confirm from which slide sir has left so that sir will continue.
Is it a problem or before that?
Just
Sir,
10 minutes, sir.
after the
10
graph,
minutes.
sir,
Eh?
region elimination graph you have shown and the condition you have shown.
No, that three principle did I explain? This first
Yes,
principle,
yes, sir. Yes, sir. Yes, sir.
these three principle already were understood, right?
Yes, yes, sir.
Okay.
Equal also you have completed.
Eh?
Equal condition also you have completed. F1 equal to F2 completed.
Okay. Then this one, this slide number 71.
Yes, this one completed.
Okay. Then this one, this
Yes, yes, from
this
yes,
one.
sir. Yes, sir. You were in this slide.
Okay. Then algorithm.
No, sir.
Okay, let us start then. So golden section method, first step is that you have to assume initial search space, that is u to v. This is for variable x. And also you have to define what accuracy you want the result, that is epsilon. This is for the x. But in golden section method, you have to define a new variable z such that this interval u to v will be reduced to 0 to 1. To do that, we have to use this expression, that is z is equal to x minus u divided by v minus u. Can you see it here? That uz, the lower bound for z will be 0 when x is equal to u, and when x is equal to v, the vz will be 1. So u to v for x is now mapped to 0 to 1 for the z. So thus the width of space for z will be vz minus uz, that is 1 minus 0 is equal to 1. Sorry. Let me put in this mode. Then initialize the iteration counter k is equal to 1. Then we select two intermediate points, Z1 and Z2, equidistant from the lower bound uz and upper bound vz. So uz plus a width, that is 0.618 times the width of the z, that is wz. Wz is the current width, right? And z2 will be from the upper bound, we go backward, so minus that width. And the width is 0.61, same width, 0.618 into wz. At these 2 points, Z1, Z2, we find out the value of objective function f, fz1 and fz2. One will compare. One will be lower, another will be higher. Then we'll apply that region elimination principle and eliminate a portion of the region, and we proceed further. We keep on eliminating such region till the interval is reduced to of width less than or equal to that epsilon, the accuracy that we require. Update this width, and the moment this wz width is less than epsilon, we stop here, and we declare that the minimum point lies between uz to vz. And again, we convert it back to x format, ux to vx, using that expression between z and x. This is the end of one iteration. So k is equal to k plus 1. Then we go to step 2 to repeat the next iteration. Let us solve an example. So minimize f of x is equal to x square plus 16 by x using golden section method, and initial interval is 0 to 5 and desired accuracy is 0.1. So given data is what? U is equal to 0, lower bound, V is equal to 5, upper bound, and epsilon, the desired accuracy is 0.1. So width of the interval will be V minus U, that is equal to 5 minus 0 is equal to 5. This is for the x, the width. We will convert it to z. So z is equal to x minus u divided by v minus u. This is the expression. So thus now uz will be 0 and vz will be 1. Like the already you have seen. So when you put at the lower bound x is equal to u, so it will be u minus u. So u minus u is 0. So 0 divided by v minus u will be 0. So uz is equal to 0. At upper bound x is equal to v. We put it here x equal to v. So v minus u divided v minus u, it will be 1. So vz is 1. So the region that is 0 to 5 for x is now mapped to 0 to 1 for z. So thus width of the space for z will be wz is equal to vz minus uz. 1 minus 0 is equal to 1. And in this expression, z is equal to x minus u divided by v minus u. In this particular problem, the value of u is 0 and v is 5. So substituting that value, this expression will be simplified to x by 5. That is equal to z, or x is equal to 5z. So since z is equal to x by 5, so correspondingly the epsilon for z, the accuracy for z will be epsilon by 5. So 0.1 if it is for x, for z it will be 0.1 divided by 5, that is 0.02. So now revise our objective function in terms of z. So since z is equal to x by 5, x will be equal to 5z. So wherever x is there, write down 5z. So x square means 5z whole square, plus 16 by x means 16 by 5z. So on simplifying this, we get 25z square plus 16 by 5z. So this is a function of z. So this is our new objective function for z. Now let us find out the two intermediate points for z, z1 and z2. These are equidistant from lower bound uz, that is 0, and upper bound vz, that is equal to 1. That's why 0 plus that width will be z1 and 1 minus the same width will be z2. And this width already you know, it will be always 0.618 times the present width. And present width is what? Wz is 1, because now the range is 0 to 1. So 1 minus 0 is 1. So putting that Wz is equal to 1, we get Z1 is equal to 0.618 and Z2 is equal to 0.382. Now let us find out function value at Z1, Z2 using this f of z, that is 25z square plus 16 by 5z. So at 0.618, we get F value 14.726. See here 25Z square plus 16 by 5Z. Z is equal to 0.618. If we put 0.382, we get 12.025. Now let us apply the principle of region elimination. So these two function value, we will start with the lower value, that is 12.025, and proceed toward 14.726. Let us see. So this is 12.025 point and this is 14.726. So we start from here and we move towards this. And this 12.025 occurs at 0.382 value of Z, and 14.72 occur at Z value 0.618. This is your Z1 and 0.382 is Z2. And these two are intermediate point in the interval 0 to 1. So proceeding from lower value 12 to 14, that means you are moving from left to right. And beyond this, and we proceed in the same direction, right direction. Anything which is beyond this higher value is to be eliminated. So this red hatched zone is to be eliminated. So thereby the current interval, that is 0 to 1, will be now reduced to 0 to 0.618 after eliminating this region. So 0 to 1 is reduced to 0 to 0.618. And see here the width is 0.618. So from 1 we are going backwards, and this is one intermediate point. And the same 0.618 we are going forward from the lower bound, from 0. So 0 plus 0.618 we get one intermediate point, 0.618. And 1 minus 0.618 we get the another intermediate point, 0.382. At these 2 points we are finding the function value. We get 14.726 and 12.025. Is that clear? How we eliminated the region and we are reducing the region from 0 to 1 to 0 to 0.618. Yes, is it clear? Any one of the participant? Please respond.
Yes,
Or
sir.
again I disconnected. Yeah. So you are on the line. Okay. So these are this golden, now we got it. Let us forget this. So see here, now the new interval is 0 to 0.618. This is, and now the width is how much? 0.01618 minus 0. So this is equal to 0.618. This is not less than your epsilon z, that is 0.02. That's why we cannot stop here. We have to proceed to the next iterations. So like this, iteration wise, we have to proceed. And this is the result we will be getting iteration wise. So we started from 0 to 1, there is uz to vz. And the two intermediate point 1, 0.618 to 0.318. And the at Z1 corresponding FZ1 is 14.726. At Z2 corresponding FZ2 is 12.025. And after eliminating, we get what? 0 to 0.618. So new uz is 0, new vz is 0.618. And from here, using again you get Z1, Z2, you will get 0.382 and 0.236. You closely observe here. One of these new intermediate point is same as one of the intermediate point in the previous iteration. See here, 0.3882 was in the iteration 1, one of the intermediate point. And in iteration 2 also, the same point has become intermediate point. But 0.236 is a new point here. So that's why in the second iteration, we need not calculate the function value at 0.382 once again, because already at 0.382 already have calculated the previous iterations. That's why at every iteration, we have to calculate only the one new function evaluation, that is at the 0.236. Compare between 2 and 3 here, you see 0.382 is common. So we need not calculate again here, only we have to calculate at 0.472. For 0.382, we need not calculate. Again 3 to 4, you see 0.382 is again common. You need not calculate again, only calculate for 0.326. Again here 4 to 5, again 0.382 is common. So we calculate only for 0.416. Between 5 and 6, 0.416 is common. See here. So we calculate only for 0.438. That means at every iteration, we are calculating the function only once. But in the first iteration, we are calculating for both. So here, if the number of it, we are getting the result here. See here, the WZ is gradually reducing. Initially it is 1, then 0.618, then 0.382, 0.236. It keep on reducing. The moment it is less than 0.02, because our epsilon 0 Z is 0.02. So 0.013 is less than 0.02. We stop it here. Then we declare that the Z star is line between UZ to VZ. So after elimination, the UZ is 0.395, and here a portion will be eliminated, and 0.048 will be the new VZ. So this will be the result. Z star belongs to 0.395 to 0.408, and this we obtained after 9 iterations. K is equal to 9. And how many function evaluation? For every iteration 1, and in the first iteration 1 more, that is 2. So that's why 10 function evaluations or 9 iteration will get this result. Now putting Z is equal to X is equal to 5Z, or Z is equal to X by 5, we can convert these values to X values, corresponding to X value. So X will be 1.976 to 2.041. So K is equal to 9 and N is equal to 10. This is the way we get the result using golden section search method. Step by step, we eliminate the region. Oh, sorry, क्या हो गया? Okay. Is it clear? Hello? How we get the result using
Yes, sir.
golden
Yes,
section method? Okay. Each and time we have to compare the value and eliminate the region. See here. So WZ is reducing like this. And which one? And you can WZ. Yeah. So this you can, this 0.618 is 0.618 to the power 1, and 0.382 is 0.618 to the power square is 0.382. 0.236 is 0.618 to the power 3, and 1 is 0.618 to the power 0. That means WZ at any iterations can be expressed as 0.618 to the power k. So 0th iteration k is 0, so WZ is 0.618 to the power k. This is the first iteration, WZ is reduced to 0.618, so 0.618 to the power 1. So in general, we can write down WZ, width of the interval for Z will be expressed as 0.618 to the power k. So width of the interval and is 0.61 to the power k. So finally, we have to keep on doing it till the width is reduced to epsilon. So the moment, so at any time width is expressed as what? Width is expressed 0.618 to the power k into 1 if it is z. If it is x, it will be, for the x, the width of the interval v minus u. So for the x, it will be 0.618 to the power k into 1 each for epsilon z. And in terms of x, it will be, in place of 1, it will be v minus u, because v minus u is the initial interval. So the moment this width of the interval is become to epsilon, we stop it there. So accuracy we can express as epsilon is equal to 0.618 to the power k into v minus u. And k is equal to n minus 1, because number of function evaluation is 1 more. So if n is number of function evaluations, is equal to always k plus 1. If number of iteration is 9, function evaluation is 1 more, that is 10. So k will be n minus 1. So this is the expression. We can, utilizing this expression, we can write down within how many iteration or within how many function evaluation you can get the result to an accuracy with the given accuracies. So if you want to get the result within accuracy of 0.001, manually to calculate will be difficult. You have to use a computer program. So 0.001 is for the x, there is epsilon x. For the z, it will be expressed z is equal to x minus u by v minus u. So if you put x equal to 0.001, epsilon z will be 0.002. So you keep on reducing it till the width of the z is less than or equal to 0.002. Then if you know these accuracies to 0.002 for z and 0.001 for x, how many iteration is required? If you want to know, then you have to use this formula. And we have seen that in MATLAB program, you will get within 19 function evaluation and 18 iterations. See here, the z value will be from 0.4 to 0, and x will be 1.999 to 2.000, because we know that x will be at 2. But golden solution method will be expressing in this interval estimate. And width of interval is how much? 2.000 minus 1.999 will be 0.0001. That accuracy 0.001. So this is all about your region elimination method. Now coming to gradient based method, let us discuss only one and then we will go to the multivariable one. So one method we will discuss, that is Newton-Raphson method. Here we start from a one arbitrary point, we move from point to point. In the earlier method, we move from interval to interval. So we assume a starting point, we move point to point, and here next point, the xk plus 1 will be current point xk minus the first derivative at the current point divided by second derivative at the current point. We keep on moving it till the first derivative is 0 or it is less than the desired accuracies. It is so small that it can be assumed to be 0. And exact differential, if you are not able to find out, we can use the Taylor series expansion to find out the first derivative. So this is the algorithm. Assume initial point x1 and maximum error epsilon, that is tends to 0. Some small value we have to, maximum permissible error, some epsilon value we have to assume it. Iteration counter k is 1. Calculate the first derivative. Calculate the second derivative at the current point. Then find out the next point is equal to xk minus ratio of first by second derivative. Hello, am I audible? Hello?
Yes, sir.
Hello? Okay, okay. Then at the next point, new point, find out the gradient, first derivative. If this first derivative at the new point is very small means less than our desired accuracies, then we stop and declare that the minimum point occurs at this new point xk plus 1. Otherwise, you will go to the next iterations. Let us solve an example. F of x equal to x square plus 16 by x and solve it by Newton-Raphson method. Starting point is x is equal to 1. Let us take it. And desired accuracy 0.1. Let us use the exact differential, exact derivative. Let us solve it first. So initial solution x1 is equal to 1. This is a given. And epsilon value is 0.1. Iteration counter k to 1. F of x is x square by 16 by x. First derivative will be x square is 2x minus 16x square. Second derivative will be 2x will be 2 and this one will be 32 by x cube. So at x1 is equal to 1, find out the first derivative. So put x1 is equal to 1. So 2 into 1 minus 16 by 1 square, we get minus 14. And at 1, the second derivative, if you calculate, will be 34. So substitute these values in this expression. First derivative is minus 14, second derivative 34, and xk is equal to 1. So substituting these, we get the next point. There is x2. x2 will be equal to 1.41176, or round it up to 1.412. At this new point, now find out the first derivative. So first derivative at this new point is coming to minus 5.204. So this is this absolute value will be 5.204. This is not less than epsilon. There is 0.1. So we have to continue. So this is the way we proceed step by step. This is the end of first iterations. So like this we can continue, and we can summarize the result. So we start with 1. Find out these two derivative. So next point is 1.412. So it next go to the next iteration. So 1.412. Again find out the two derivative. So the next point will be 1.802. So still the first derivative is not less than 0.1. So we have to proceed. Absolute values. Each 5.2. So we proceed. So 1.801. Again find out two derivative, first and second. Next point is 1.978, and at 1.979, first derivative is 0.128, still not less than 0.1. So you have to proceed. So first and second. Next point is 2.000. At 2.000, first derivative we found out minus 0.001. Its absolute value is less than 0.1. So we stop it here and declare that minimum point occurs at x is equal to 2. Understood? How step by step we can use Newton-Raphson method and find out the solution. The minimum value of f will occur at x is equal to 2. So this is all about Newton-Raphson method. Suppose a function is not, this is a very simple example I have given, which the derivative first and we are able to find out. If you are not able to find out the first and second derivative, we can use the Taylor series expansion, the central difference method, and find out the first derivative. So first derivative will be f of x plus delta x minus f of x minus delta x. Delta x will be 0.1% of your x values, absolute values of x. And if x value is less than 0.01, the 0.01 is your delta x. So the minimum value of delta x will be 0.01. If x value is more than 0.01, you take the 1% of that, will be delta x. And x plus delta x, you find out f value, x minus delta x, you find out the f value. Take their difference. Because first derivative is nothing but the rate of increase of the function values with respect to the increase in x values. So between these 2 points, x minus delta x and x plus delta x, the width is 2 delta x. So divided by the change in x is 2 delta x. Change in f of x is the numerator. So the ratio will be first derivative. And the second derivative will be by this formula. Bottom will be delta x square and this one will be the numerator. So when derivative we are not able to differentiate, use this expression to find out this first and second derivative. Then use the Newton-Raphson method and get the result. So this is the same example. We are using by approximation method. So here x1 is 1, which is more than 0.01. So that's why delta x will be 1% of this x1 value, 0.01 into absolute values of x1. So absolute value of 1 is 1 into 0.01 is 0.01. So now take 2 points. x1 plus delta x1 is 1 plus 0.01 is 1.01, and x1 minus delta x1 is 1 minus 0.01, 0.99. At these 2 points, find out the function values. So if 1.01 function value is 16.861684, At 0.99, function value is 17.141716. And at f of x is f at 1 equal to 17. Now let us find out the f of first derivative. So these two difference, put these values, and delta x1 is 1, we will get minus 14.002. And double derivative, putting these values, f of x is f of 1, x plus delta x already calculated, x minus delta x already calculated, we get 34.003. And again, using these two values, we will get the next point x2 is equal to 1.412. Same way we can proceed. And at this new point, first derivative is minus 5.202, whose absolute value is not less than 0.1. So we have to proceed. So this is the way we continue till we get the result. So this is the result. And here you see the first derivative at 2.00 is 0.001. His absolute value is 0.001, less than 0.1. So we stop and write down that at x equal to 2, the value of function value will be minimum. So this is the Newton-Raphson method using inexact differential, and the other one is by using exact differential. So if it is differentiable, use the first method. If not differentiable, use the second method. That is Taylor series expansion method. Now, whatever we have read it till now, if you have not understood anything, no problem. Use this. All this optimization tool is available in our MATLAB toolbox. Use these 4 commands and you can still find out the optimization result. If it is single variable, use fmin bnd, and if it is multivariable, use these 2 variables, fmin search and fmin unc. This is called unconstrained. And if it is a constraint problem, use fmin com. So if you use these 4 subroutine in MATLAB optimization box, you can solve any problem, single variable or multivariable. Excuse me, let me drink some water. My throat is getting. Let us have a break for 2 minutes.
Okay, sir.
Okay, let us start. So let us use the MATLAB subroutine fmin bnd, how we can solve a single variable problem. So this is the problem. So lower bound is given u is 0, upper bound is v is 5. Then in MATLAB command, just write down this command, you will get the result. The square bracket open, x1, comma, write down fun bl, comma, exit flag, comma, output bracket close is equal to this fmin bnd, this subroutine name, write down, bracket open, then write down your objective function. That is x square plus 16 by x, so apostrophe open, x square is x dot x, so star before that put a dot, plus 16 by x is 16 dot divided by x apostrophe close. Then put a comma, then write down the lower bound of x, that is 0, comma, upper bound of x, that is 5. If you press enter here, you get the result. Or you can also use, you can invoke the optimization toolbox by writing a command called optim tool. Or in the menu, you first click apps, then click optimization. You can also invoke the, hello? See here, in the top one, there is apps button. First click apps, then click this will pop up. In that optimization, you click, you can invoke the, this window will get it. But in the latest version, this window is not there, this type of optimization toolbox window, right? So there also you can select admin BND and you can able to solve it. So let us not discuss this, because in the latest version this feature is not available. You write that command prompt and you can get the result. This is all about your single variable optimization problem. First we discussed analytical method, that calculus method. Then we discussed numerical method. In that we first discussed the exhaustive search method. That is a bracketing method. Instead of exhaustive search method, we can select that bounding fetch method. Then we improve the solution using either region elimination method. In that we discuss golden section method, or gradient based method. There is a Newton-Raphson method. And finally, we have used how in a MATLAB ready-made command that f mean BND, utilizing this we can also solve the single variable problem. Now let us go to multivariable one. This is all about single variable. We'll go to multivariable. Is my visible now slide? Hello?
Yes, sir.
How to make it?
So make the slide in presentation mode.
Yeah, making it. Yeah. Okay, so multivariable optimization. Here the number of decision variable will be more than one. So you have to search in multi directions. And all the algorithm, whatever we are discussing for minimization, using that you can also solve any maximization problem just by modifying the objective function. So maximization of Zx is as good as minimization of minus Gx. So algorithm is same for both maximization and minimization. Just you have to modify the objective functions. So here also there are two groups of methods. Direct search method. Here no need of any derivative. Only you have to find out the function value and compare. But in gradient based method, you have to find out the you have to take the help of first and second derivative. These are the four direct search method. Already I have told you at the beginning. We will discuss today this Hooke's Gibbs pattern search method. And gradient search method, already I have told you, these are the gradient based method. So Cauchy's method is more popularly used. Let us first try to understand two, even if you MATLAB, these two expressions, this we must try to understand. One is first derivative, another is second derivative. In multivariable problem, the first derivative is called gradient vector. That is denoted as del f x. So here the decision variable will be more than one value. There is x1 to xn. So it is always a set of values. So x1 to xn, there are n number of unknown variables. So this we represent as a vector called x, vector x. And in sometimes we represent either x, vector x or bold x. In the book, usually you write the notation bold x. So the objective function will be f of x1 to xn, or it is also can be represented as f of vector x or f bold x. And first derivative of this multivariable objective function is denoted as the gradient vector, that is del f x. This del is inverted triangular. Del f x is not a scalar, it is always a vector, it is a matrix. So here we take the partial derivative of first order with respect to each of the unknown variable. So set of all these n partial derivative will constitute the gradient vector. So gradient vector is nothing but first order partial derivative, each one with respect to each unknown variable, del f del x1, del f del x2, del f del xn. And double derivative will be, it will be n by n matrix, that is denoted as del square fx. It is also called as Hessian matrix. So this is del of del x1 of the which one? That we have taken the gradient vector, del f del x1 to del x1. The gradient vector, if you take with respect to another derivative with respect to x2, this is the second row. Similarly, the nth row, last row will be with respect to xn. So each time what you do, the gradient vector is to be again differentiated with respect to x1, it will be first row. With respect to x2, it will be second row, like this up to nth row, that will be your Hessian matrix, del square fx. So simplifying this, we get these values for Hessian matrix. Now let us first discuss analytical method, just like single variable. Then we will go to the numerical method. So here also it is same. In a multivariable problem, the point vector x will be a stationary point if of objective function f of x if the first vector, first derivative, there is gradient is 0. First we solve the first derivative, there is gradient is equal to 0, we solve it, and then we will declare whether it is minimum, maximum or point of inflection based on the Hessian matrix. If it is positive definite or negative definite or otherwise. It is not simple definite, we call it positive definite. It is not simple negative, we call it negative definite in the language of the multivariable problem. Let us try to understand by taking an example. Let us take a multivariable problem. This is a two variable problem, x1 and x2. Number of unknown is 2. And f of x is like this. This is a Himmel-Blau function, very popular one. And you have to find out, check whether 3, 2, when x1 is 3 and x2 is 2, whether f of x is a local minimum. You have to check it. So what is the first one? You have to find out the gradient vector. So for gradient vector, we need two partial derivative. One with respect to x1 and that is x2. There is del f del x1 and del f del x2. So f is like this. F of del x1 will be, we have to first take the derivative of first one. So here with respect to x1, keeping x2 constant. So here it is a addition of two expressions. So for the first one, it will be twice of whatever is there inside, twice of x square plus x2 minus 1 into derivative of what is there inside. We have to take the derivative with respect to x1. So for x1 square, it will be 2x1. x2 is to be assumed to be constant while taking partial derivative with respect to x1. So for x2 it is 0 and 11 is a constant, so it is 0. Now for the second term, again twice into whatever is there inside into the derivative what is there inside. So for x1 it is 1, for x2 square it is 0, where x2 is constant, and 7 it is 0. So on simplifying we get this one. So this is the del f del x1. Now for del f del x2, so twice whatever is there inside, then whatever there inside you have to differentiate with x2. So x1 square is now constant, so 0. For x2 it is 1. For 11 it is 0. Then for the second term, twice into whatever is there inside into differentiate the inside. So for x1 it is 0, x2 square is twice x2, or minus 7 it is 0. On simplifying we get these values, these expressions. So this is gradient vector. So this is at 3, 2. Let us now find out the value of gradient vector. So let us substitute the value x1 is equal to 3 and x2 is equal to 2. So we get 4 into x1 is 3 into x1 square, 3 square, plus x2 is 2 minus 11, plus 2 into x1 is 3, x2 square is 2 square minus 7. When you simplify, you will get 0. Similarly, putting x1 is equal to 3 and x2 is equal to 2, we get del f del s2 also 0. So since both the partial derivatives are 0, we can say that the gradient vector is equal to a null vector, 0, 0. So this 3, 2 is a stationary point. That means at 3, 2 may be a local minimum, may be a local maximum, or point of inflection. To decide that, you have to take the Hessian matrix, del square fx. Let us find out that. So Hessian matrix is this one. So let us find out. So if f is this one, del square f del x square will be del of del x1 of del f del x1. Del f del x1 already you found out. Once again you find out with respect to x1, we get these expressions. And putting at 3, 2, this del square f del x1 square will be 74. Similarly, finding out the other 3 expression, it will be del square f del x2 del x1 will be 20 at 3, 2. And del square f del x1 del x2 will be 20. And del square f by del x2 square will be 34. So thus at 3, 2, the Hessian matrix will be Hessian matrix will be 74, 20 and 34. Del square f is ACBD, where A is 74, B and C are both are equal, that is 20, and D will be 34. Is that clear? At 3, 2, del square f will be 74, this C will be 20, and this B will be 20, and this D will be 34. Now let us try to understand what is a submatrix and a minor. So this is a 3 by 3 matrix. This A is 3 by 3 matrix. So its submatrix of kth order, if A is of n by n matrix, its kth order submatrix will be obtained by deleting the difference. N minus k row you have to eliminate, and n minus k column you have to eliminate. If you eliminate any n minus k rows and any n minus k column, then you will be left with kth order submatrix. And the determinant of this submatrix is called the minor. But instead of deleting any row, any column, yes, anything? Okay. If you select any n minus k row and the corresponding n minus k column, then you will be getting principal submatrix and its determinant is principal minor. But if you delete last n minus k row and last n minus k column, we will be getting leading principal submatrix, and its determinant will be leading principal minor. Let us take an example. So here we are deleting last 2 column and last two rows. So we are left with A11. So this is a leading principal submatrix, and its minor, its determinant will be A11 only. So A11 will be leading principal minor. To get second order LPS, leading principal submatrix, so K is equal to 2 and N is equal to 3 by 3 matrix is A. So N is equal to 3. You have to delete N minus K rows and N minus K column. So N is 3, K is 2. So N minus K will be 1. So you have to delete one row, one column. Just excuse me for a moment. Hello? हम गोटे क्लास रे अछि ऑनलाइन क्लास 9टा परे तिके कथा हेबा ना ओके so here we are deleting last row and last column, so we are left with A11, A12, A21, A22. So this matrix is a leading principal submatrix of order 2 by 2, and its determinant will be leading principal minor. To get third order LPS means K is equal to 3 and N is equal to 3. So 3 minus 3 is 0. So delete 0 rows, 0 column. Means don't delete anything. Means the same matrix will be leading principal submatrix of third order. And its determinant will be leading principal minor. So these are all, this is the first order submatrix, leading principal submatrix. This is the second order leading principal submatrix. And this is the third order submatrix. That means this red color is LPS of first order, red color and this blue color will be leading principal submatrix of second order, and all these elements are of the third order. So we are starting from this corner point and we are proceeding towards like this, towards the right and down. So these are submatrix, principal submatrix and LPS. So out of this 3 by 3 matrix, we will get 9 submatrix of one order, 3 principal submatrix, and 1 leading principal submatrix. Similarly, second order will get 9 submatrix, 3 principal submatrix, and 1 leading principal submatrix of second order. And third order, we will have this one, which is submatrix, principal submatrix as well as leading principal submatrix. I repeat again, the difference between principal submatrix and leading principal submatrix is that in leading principal submatrix we are deleting the last rows, last column. Hello? And in principal submatrix, whichever rows we are deleting, the same column we have to delete. If second and third row we are deleting, second and third column we have to delete. If first and third column we are deleting, then first and third rows we have to delete. That is principal submatrix. And in submatrix, any rows, any column, you can delete second and third rows and first and third column. Then we get a submatrix. Okay, let us solve it this one. So the same problem at 3, 2, we get first gradient 0, 0. And this is the Hessian matrix at 3, 2, 74, 20, 20, 34. So here, leading principal, all the leading principal minor, you have to find it out now. So since it is 2 by 2 matrix, we will have 2 leading principal submatrix. One of first order, that is 74, and of second order, there is 74, 20, 20, 34. Let us find out the determinant. 74, the determinant will be 74, and 74, 20, 20, 34, the determinant will be 74 into 34 minus 20 into 20, it will be 2116. Since all these 74 and 2116 means all the leading principal minor, there is 74 and 2116 are positive, so we can declare that this Hessian matrix is positive definite. Since all are positive, strictly positive, so leading this Hessian matrix at 3, 2 is positive definite. So we can write down that since it is positive definite, 3, 2 will be local minimum. So earlier we discussed analytical method for single variable, this is for the multivariable. In multivariable, we have to find out first derivative, which is gradient vector, and we don't have to find out third order, fourth or second order, third or fourth order. We have to just find out the Hessian matrix. That is second order. This is Hessian matrix. In that we can, and then find out for the Hessian matrix all the leading, principal, minor. If all are positive, it is positive definite, will be minimum. If any of it is negative, then it will be negative definite. 3, 2 will be maximum. So now let us discuss one of the numerical method. There is Hook-Gibbs pattern search method. It consists of two moves. We start from any arbitrary point, and every iteration it has two moves. When it is exploratory move, we will explode in the locality of the current point, and then we take a jump from the current point to the next point based on the pattern on which it has been established. So in exploratory move, if the current point is here, every direction we have to search. So let's say in this direction, we take one forward step, that is C plus delta, and one backward step, C minus delta. And at 3 points, we find out the function values. At the current point, it is F. At the ahead point, it is F plus, F of C plus. And in the back point, it is F minus. These three values we will compare, whichever is less and more, and accordingly we take a decision. This is exploratory move. Whichever is, since objective is to minimize, whichever is minimum, we have to move to that point. Similarly, we select in the all the direction we will search, and then we proceed. Then in the pattern move, the next point to which we will move will be current point plus the difference between the current point and the previous point, xk minus xk minus 1. So based on this difference, we take a next jump from the current point. So wherever we will end up, that is the next point after the pattern move, xp xk plus 1. So these are all the algorithm. Let us go to the example so that you can understand directly. So we'll minimize this f of x. This is a two variable problem using Hook-Gibbs pattern search method. Initial point we start from 0, 0. There is x1 0, x2 0, and then increment vector is 0.5 in x1 direction, 0.5 in x2 direction. Step reduction factor is 2, means half we will reduce, and desired accuracy is 0.1, 1 decimal point accuracy. So let us start from the current point. There is 0, 0. x0 means current point. At the 0th iteration, you are at 0, 0. So here 0 we are putting at the top, means it is 0th iterations. And the step vector is 0.5, 0.5. Step reduction factor alpha is 2, and desired accuracy is 0.1. Iteration counter k is equal to 0. Let us do first one. So first we search in the x1 direction. So we assume x2 is equal to constant. So x2 is equal to 0 is constant. So in current point x1 is 0. So you change only x1 values. So forward point will be 0 plus 0.5 is 0.5. And one backward point, 0 minus 0.5 means minus 0.5. At these 3 points, assuming x2 is 0, you have to find out the value of f. So see here, for all these 3 points, x2 is 0, 0, 0. We are changing only x1 value. So x1 0 is the current point. x1 0.5 is the ahead point, forward point, and x1 minus 0.5 is the behind point. That is, so at these 3 points, find out the value of f, the Timmel-Blau function. x1 is 0, x2 is 0, minus x11 square plus x1 plus x2 square, x1 0, x2 0, you get 170. But x1 square, if you put x1 is equal to 0.5 and x2 0, here x1 0.5, we get 157.81, and here we get 170. At 3 points, you get 3 different values. So which one value we should select? Yes, anyone? Whichever is minimum or maximum. Hey, are you there or left? Hello?
Yes.
Okay. So, which point we should select out of these three value? Whichever is minimum. Why? Because your objective is to minimize. Okay. So, here the minimum value is 157.81. So, we select this point. So, we move to 0.5, 0. So, we are now at 0, 0. We move to 0.5, 0. Is that clear? Minimum is 157.1. So from 0, 0, we move to 0.5, 0. So with this, we search, we explore in x1 direction. But it is a two variable problem. We have another direction, there is x2. So now we will search in the x2 direction. That means we will now vary only x2, keeping x1 constant. And what is x1 now? x1 is 0.5. So x1, we keep it constant at 0.5 and we change x2. One forward, one backward. So from 0, we will take one step ahead, 0 plus 0.5, one step back, 0 minus 0.5. So this is the 3 point. That is keeping x1 0.5 constant. See here, current point 0.5 x1. One step ahead also x1 is 0.5. One step back also x1 is 0.5. But x2 value is at the current x2 is 0. One step ahead x2 is plus 0.5. One step back x2 is minus 0.5. So at this 3 point, again calculate the function value. We get value 157.81 at the current point, 144.13 at the ahead point, one step ahead, and 165.63 one step back. Comparing these three values, the minimum value is 144.13. That occurs at 0.5, 0.5. So we have to move to this point. So from 0.5, 0, we move to 0.5, 0.05. So we have searched now in x1 direction, also search in x2 direction. With this, the exploratory move is over. Now we have to go for the next move, that is pattern move. And here we land up in a different point, new point. We started with, before the exploratory move start, we were at 0, 0. At the end of exploratory move, two stages. One is x1, another is x2. We landed at 0.05, 0.05, which is different than initial point, that is 0, 0. So it is a success. Now go to pattern move. So here pattern move will be, previous point is 0, 0. Okay. So this 0.05 is your x1. If x0 is 0.00, this 0.5, 0.5 will be x1. Here, since we do not have any previous point, we cannot establish any pattern. So in this iteration, we will have only exploratory move, no pattern move. Because before 0, 0, we don't have any other point. So we don't have any scope to establish a pattern in the previous one. So 0.5, 0.5 is your x1. Now we go to the second iteration. So first we do the pattern move. So between these two moves, 0.5, 0.5 with 0, 0, let us establish the distance. So x1 minus x0. x1 minus x0. That distance will add it with the current point x1. So see here. So the formula is xp k plus 1. So k is here 1. So xp2 will be equal to x1 plus x1 minus x0. Current point minus previous point. So on simplifying, we get x1 plus x1 is 2x1 minus x0. So now x1 is what? 0.5, 0.5 and x0 is 0, 0. So 2 into this one will be 1, 1 minus 0, 0. So we will get 1, 1. This is just matrix multiplication and addition, subtraction, nothing else. So 1, 1 will be your next point after pattern move. That is xp2. From 1, 1, now we have to do one exploratory move. Let us do it. So from 1, 1, keep x1, 1 constant. No, sorry, x2 constant at 1, and x1 you vary 0.5 plus 0.5 minus. So 1, 1 will be current point. 1 plus 0.5, 1.5 is one step ahead. 1 minus 0.5, 0.5 is one step back. And all the 3 point x2 is constant at 1. Again, find out the function value. We get these 3 value. In this 3 value, minimum is 18.31. So we move to this 1.5 comma 1. This is after the search in the x1 direction. Then we search in the second direction, in the x2 direction. And here we'll put x1 constant at 1.5 and we'll value x2. So see here, in all the 3.1, x2 is 1.5, 1.5, 1.5, x1. And x2 is very 1, 1.5, 0.5. Again, you got 3 value. Minimum is 63.13. So move to 1.5, 1.5. So this is the end of exploratory move. So we completed the second iterations. Now you go to the third iteration. There we will do first pattern move, then exploratory move. So x2 is 1.5, 1.5. This is a new point. Now we have to compare this function value at x2 and x1. At x2, function value is 63.125. At x1, function value is 144.125. So value is falling, decreasing from 144 to 63. So we are proceeding in the right direction. So we continue. So now let us, in the third iterations, let us do the first pattern move, then exploratory move. So xp3 will be equal to now, xp3 will be x2 plus x2 minus previous one, x1. So this will be x2 plus x2, 2x2 minus x1. So substitute the value x2 and x1. x2 is 1.5, 1.5, x1 is 0.5, 0.5. We will get at 2.5, 2.5 at the end of pattern move. Now we'll do another exploratory move from this 2.5, 2.5. So first along the x1, we get again 3 value. Minimum is 5.31. So move to 3, 2.5. Then x2, we have kept 3 constant, only x2 value we have varied. We get 5.31, 26, 0. Minimum value is 0. So we move to 3, 2. At 3, 2. Then we compare x3 with x2, their function value. So at fx3, at x3 f value is 0, at x2 f value is this one. So from 63 it is reduced to 0. So we proceed, we are reducing. So proceeding like this, then again we'll go to the xp4, we get 4.5, 2.5. Then we do exploratory move, we go to 4, 2.5. Here 66.81 is minimum. Then at x2 we go to 4.2. So this is the end of this one. So at 4.2, the function value is 50, but at x3 function value is 0. So for the first time, the function value is now rising. You see, from 0 to 50 it is increasing. So now we want minimum value. So don't proceed further because we have observed that function value is rising. So we stop here and check whether the termination has come. So now we check this. What is the double bar? This double bar is nothing but norm of a vector. So norm of a vector is nothing but square root of x dot x dot. So x dot will be x1 square plus x2 square, x2 square. Let's say the vector x. Yes, madam. Hello. Oh, it is exactly 9. So let me take another few minutes. I will complete. Only 5 minutes we will take and then we will close it down. So if vector is 1, 2, the norm of vector 1, 2 will be what? 1 square plus 2 square, square root will be square root of 5, 2.236.
Okay.
Okay. So if norm of a that step vector is less than the desired accuracy, we will stop. So let us find out. Our step vector is 0.5, 0.5, and its in norm will be 0.5 square plus 0.5 square. It will be 0.707. This is not less than your epsilon value 0.1. So we will not, then since we will not stop here, right? So now we have to decrease this step vector. This 0.5, 0.5 will be reduced by divided by 2, alpha is 2. So now it will be step vector will be 0.25, 0.25. So be at 3, 2, where the function value is minimum, the less, and then we have to do now exploratory move with step size not 0.5, 0.5. You're taking step size 0.25, 0.25 with reduced step size. So let us try. So from 3 to taking step size 2.2.5, we will be getting again 3 value in x1 direction. So minimum value is 0. So you stay at 3, 2 because other things are higher value. Let us search in x2 directions, keeping x1 constant. Again 3 value. Again we find 0 is minimum value, that is at 3, 2. So you remain at 3, 2. Don't move here and there. You are getting higher values. So we not get any new value, EM is a failure. So now again you check this step vector, the norm. So 0.25, 0.25 is your step vector. So its norm will be 0.3565. Again it is not less than 0.1. So again you reduce it. So by half it will be 0.125, 0.125. Again try. So again do the exploratory move with step size 0.125. Again you will see it will not increase from 0. So you remain at 3, 2. Again x2 direction, again the minimum value is 0, it is at 3, 2. So remain at 3, 2. Again EM is failure. Again find out the norm, you will find 0.1768. Still not less than 0.1. Again reduce it by half. So now it is 0.0625, 0.0625. Again do exploratory move. Again minimum is 0, be at 3, 2. Again x2 direction, again minimum is 0, remain at 3, 2. Don't move here and there. Be at 3, 2 where function value is 0. Again find out the norm. Here for the first time we get the value is 0.08, which is less than 0.1. So we stop here and declare that the minimum value occurs at 3, 2. So this is all about your Hooke's method. So this is the way I moved it. We started at 0, 0. Then 2 exploratory move, x1 direction, x2, we move it here. This is x1. And then we take a jump x0 to x1. This is the difference, x1 minus x0. In the same, we join from x0 to x0 and move in the same direction by same amount. This is pattern move, xp2, 1, 1. Again x1, x2 is x2. Then we have compared x2 with x1. So 63 is less than 144. So we proceed further. Then x2 minus x1. So from x1 to x2, this is the jump. Same jump, we proceed in the same direction, xp3. Again x1, x2, we end it here. So here a function is 0, here function value is 63. So we come here, prefer. Again we proceed, then we get from x3 to x2. So this is that difference. Jump in the same direction, we get it here, xp4. Again x1, x2, xp4. Here value is 50, more than 0. So don't go there, again come back to 3, 2. Here we have explored it with reduced reduction and finally declared that at 3, 2 is the optimum point. So this is all about your multivariable optimization algorithm. And here same optimization toolbox for multivariable, use fmin search, fmin UNC, you can search. Earlier you used fmin BND. Now you can use these two, you can solve the multivariable problem. So these three is for unconstrained problem. If there is a constraint, you can use a min con and you can get the solutions. Okay, with this we can conclude. If any doubt, you can tell me. So we have learned today both single variable, multivariable, and in each case we have learned analytical method, that is by differential derivative, and numerical method. In numerical method, we have learned which one? That direct search method and gradient based method. In multivariable also we have learned like this, and at the end also the optimization toolbox or MATLAB. Using this 4.1, you can use any single variable, any multivariable, whether unconstrained or constrained, you can get the solutions. Okay, thank you. Any question I can clarify, otherwise we will conclude here. Hello.
Thank you, sir. Thank you, sir.
Okay, it is already 9:10 now.
Yes, sir.
Thank you,
So
sir.
the participants are encouraged to clarify the doubt by email or WhatsApp, but they are advised to first watch my video lecture. All these lectures are available in the YouTube video lectures. Thank you.
Thank you, sir.
Thank you.
So no doubt then I can log out.
Yes, sir. Yes, sir. Thank you, sir. Good night, sir.
Okay, good night. Thank you, Madam, BC Madam, for giving me this opportunity. And thanks to all the participants for patient hearing.
Thank you, sir.